Okay, last class, I promised I was going to tell you a different method. Some of you have taken circuits from lots of different people. So if you just hate circuits in general, I know most of you are mechanical, okay. Follow the last stuff that we did. If you really don't feel comfortable with circuits, I would say the last method we talked about last class is a better option. But the impedance method is another way of looking at circuits which gets to the transfer function. So if you understand it, you can typically get to the transfer function a little bit faster. But again, it might be a little bit hard to understand. So I'm going to introduce it, and then we'll do some of the similar problems we've looked at before. So the transfer function and impedance. The definition of impedance is really just resistance. So obviously resistors resist the current flow, but capacitors and inductors also have their own impedance. They do slow the current down a little bit, just how they're set up. So in an electrical system, impedance is the generalization of the ratio of the voltage transform to the current transform, and we give it the symbol Z. Notice we're already in the S domain. So impedance is already taking all this time domain stuff and turning it into S's. And so from there, once I change those definitions, I can kind of add different things together. I can combine them until I get to my transfer function. So if the impedance is equal to the voltage transform over the current transform, what is the impedance of a resistor? What would you say it is? Huh? Ohms, yeah, or R. So the impedance of a resistor is just R. Yes, the ohms. What if it's a 1 kilo ohm resistor? It's 1 kilo ohm. That's the impedance. It's just equal to the resistance. Now, on the equation sheet, there's also these definitions. So impedance of a capacitor is 1 over CS. So there's our operator S. And then impedance of an inductor is L times S. Now, these might look like they're out of left field, but they actually come, we can derive them from the equation sheet. For example, the equation we just used last time in class, which, if I'm doing it the other way, I can look at the current I know is equal to C times the derivative of EC, how that voltage is changing with respect to time. If I put this in the S domain, dot becomes S. So if I change my dots to S's, it gives me this. And then if I want to find the impedance, impedance is, like just over here on the left-hand side, voltage over current. So voltage over current equals 1 over CS. So these are on the equation sheet, so you don't have to memorize it. You don't have to derive this each time and do your own Laplace transform. You don't have to do that. But that's how they're related. It's all, both of these equations have relationships between current and voltage, and therefore we can get the impedance like that. So we're just doing a quick change, and those are our 3 definitions. Questions? Well, we will do quite a few problems, at least 3 or so. Oh, no. Whatever. You saw it worked out. Okay, why is it useful? Well, we can combine individual impedances with series and parallel laws to find the impedance at any point in the system. So I can combine them just like I combine resistors. So instead of having, capacitor, instead of having inductor, those are all going to change to having impedance. So I can just redraw them all as basically resistors. And then for any resistors that are in series, I can just add them together. Any that are in parallel, if you remember how to add resistors in parallel, we're going to do 1 over Z equivalent. So we're adding all the reciprocals, and we take the inverse of that to find the equivalent impedance. Some other checks that's helpful: impedances in series, they all have the same current. So if I've got a line with a couple different elements, they all have the same current. And if they're in parallel, the total impedance between those two wires, wherever it splits, they should have the same voltage difference across that total impedance. So we still have the same KVL, KCL. Those laws all still work, and for some problems you have to use it. This can be a little bit faster for some applications, but if you don't feel comfortable with it, I'm not going to make you ever do this. It's just option number 2. Does that make sense? Yeah? Just making sure people are listening. All right, let's almost try a problem. So quick recap before we try a problem. It can be quicker if you understand it to get to a transfer function. Impedances just add like resistors. And so here's our definitions, which are on the equation sheet, which again, impedance is just the voltage transform over the current transform. So we should be able to solve for any part. Let's do a problem. Now, using this method, okay, you still want to use bow body. So bow body isn't changing except until we get to the D's. When I get to define, when I get to diminish, that's where it's going to change. So if you go back in your notes a little bit, we did this problem, example 3.1. So we did the first couple. We saw it was first order. We have the input was En. The output was the current. So we did all those first steps just to figure out, where this equation is going. But now we get to the definition, and this is where we can split off. When it comes to homework, when it comes to tests, I don't care which method you choose. If you like this one more, use it. For the definitions, now I'm going to put for my inductor, the impedance of an inductor is equal to Ls. The impedance of the resistor is just equal to R. So I can redraw this still have the same current going through all of it. I'll change that to capital. When we're using impedance, we are doing a Laplace transform. So I can combine L and R. I can just treat them as resistors. If they're resistors in series, we can just add them together. So Z equivalent is equal to the impedance of the inductor plus impedance of resistor, because they are in series. I'm just going to add them up. So that equals Ls plus R. Did I lose anyone? Any questions? Okay. So now when I'm looking at this problem here, the relationship between EN and IL. My ultimate goal is, because input is EN, output is IL, I want a transfer function. The end goal is to get output over input. So, what is that? Well, if I do kind of a case KVL around here, KVL, I have EN minus the voltage of Z equivalent gets me back to 0. So EN is equal to the voltage across that equivalent impedance, which is equal to the impedance times the current. So with the impedance method, you're still going to use KVL, KCL. And look, the way that you learned it could be very different. I know that some people they look at it slightly different, especially Rodriguez. He looks at these much differently than I do. But we should get to the same answer because now I know the equivalent. So En is just equal to Ls plus R times the current. So now I can set up my equation. I divide both sides by En. I divide both sides by the polynomial. We get 1 over Ls plus R. That matches what we did last time in class. Does it look different? It looks a little bit different. Maybe it's a little bit faster. I don't know if it's faster. The other one might have been faster in this case. As they get more complicated, the more I can simplify it like this, it usually becomes faster, only if you know how to do it. Questions? Shall we do another example? Okay, that one was pretty easy. So we're going to do another example here. We're going to do this one together, and then I think you're going to try one out yourselves. So together, this circuit looks a little bit different. We want to find output voltage as a function of input voltage. What method should we follow? Let me see. Full body. I'm going to put 3 steps together on this slide. Can you tell me the order of the system? First order. I have one capacitor, therefore it is one first order equation, which means it's one first order transfer function, which means 1s. No s squares, anything like that. Okay, body diagrams. So I have this body diagram here. Can I, if I change this capacitor to a resistor or impedance, is there a way that we can simplify this? Yeah? So we could take this, here's my supply voltage, and we could create one equivalent impedance And so instead of having 3 different currents, this is also the helpful thing about this. Instead of having to care about I1, I2, I3, we're just going to have one I1 going through here. That's the same current going through the equivalent, going through R1, finishing up that loop. Right? Now, we'll talk about later, is there a way we can even simplify this a little bit more? It's possible. Anytime I've got my output like this, output is related to that resistor 1, so it's not like I want to just combine it all at this point. We'll see what we can do down the road. But that is, when I get to my definitions, then I'm going to, have to describe what that means. What is Z equivalent? And, for a lot of these, you could draw 3 or 4 different diagrams. Maybe you start with the simple one. Okay, I'm going to combine these two. Then my next step, I'm going to combine these two. So you could draw it a couple different times just as you go if you want to. Lastly, we're going to do inputs and outputs. I think we all know what the input is. It's going to be supply voltage. And what is the output? It is V out, yes. So anytime I've got an output voltage, that's my output. Whereas if I don't, then they have to either say maybe that they give you a transfer function they want. In this case, if I didn't have an output voltage, my output would be capacitor voltage, E sub C. Yeah. Correct. Well, if they don't tell you what the transfer function is, we're always going to use the output voltage because that's like output over input. I guess we could always model it to be in terms of capacitor voltage. We could always look at what is that voltage with respect to input. But the default would be output voltage. So it is possible to model both of them. They're going to be different equations, but we're going to do the output voltage every time that it's shown. Okay, so we've got the first 3 steps down. I forgot to breathe, but whatever. Now we're going to go on to our definition. So this is where we're going to use our equation sheet. We have to define this, and then we'll actually start putting together some KVLs, KCLs, just like the other method. Questions? All right, so first off, I have a capacitor. Capacitor impedance is 1 over CS. Resistor is just R. And so again, let me just draw this real fast. We combine these into one equivalent impedance. So I've got I1 coming through here. Here's supply voltage. Equivalent impedance R1. This is my output voltage. So we have to define Z equivalent using those two. And Oliver, you were saying, how do we do that if they're in parallel? Yeah, so for parallel, it's going to be 1 over Z equivalent equals. So we're going to add all the reciprocals together. So I've got a impedance of, that's R2. And I have an impedance of C, capacitor. A lot of people make mistakes with this. Sometimes they try to do too much in one step. I would suggest, just like with all of a body, to write it out and take your time because it's easy to mess this up. Because they're in parallel, I got to make sure my left-hand side is also a reciprocal, 1 over Z equivalent. And then I put in the Z's first. So what does Z R2 become? Or 1 over Z R2 should be 1 over R2. Yeah, resistor is easy. What should 1 over Z C be? Just CS. Yep. So that's a 1 over CS. So that just flips it. So now I have 1 over R2 plus CS. I want to combine this. I don't want to keep it separate and then try to work with it going. I just want to get one nice numerator denominator. So one way to do it is to get a common denominator. So I can multiply this by R2 over R2, which is the same as multiplying it by 1. And so we have R2 CS plus 1 over R2. So we now have our equivalent impedance. Do we? Is this our equivalent impedance? Is this Z equivalent? Thank you. It's not. I gotta flip it, right? So that's 1 over. So really my Z equivalent is R2 over R2 CS plus 1. And be really careful. What I noticed on some of the homework is like forgetting 1s and 2s. Those matter. Not all the resistors are going to be equal. So making sure we've got everything listed properly. Okay. Now, I think we're closer. Do you have any ideas of what the next step should be? No. KVL, great. Let's do the loop. If this is loop 1, KVL is a great idea. So KVL 1 is we have supply voltage coming in. We've got, I can say voltage of Z equivalent, the voltage across R1. This gets me back to 0. So that's one complete loop. So we can say that supply voltage equals the voltage across Z equivalent plus the voltage across R1. Okay. Now, because we were able to simplify the circuit with Z equivalent, I just only have one current going through the loop. And so we can actually write this as supply voltage equals Z equivalent times the current. We're all in the S domain, plus the voltage across the resistor, which is R1 times the current. And so we can actually combine these. Z equivalent plus R1 times the current. So yeah, same KVL. We're able to simplify it using Z equivalent. I have it here. I have Z equivalent. So actually we can Z equivalent plus R1. Now again, I want to combine all of it. So if I'm going to add R1 to this, I need to have a common denominator. So I'm going to multiply basically denominator to R1 to be able to add it there. So what we end up with is R1, R2, CS plus, and then I have a 1 times R1. We're going to add that over there. So we get R1 plus R2 all over that same denominator. So I would just recommend doing it now, not just keeping it as, let's say, R2 over R2 CS plus 1 plus R2, or sorry, plus R1, and just keeping it till the end. I like to try to work it out as I'm going, and that way, when I get to the end with my transfer function, I don't have to like do 10 steps in one, trying to make it right. Now I have, this is my, you can think about it as the total impedance here for that loop. That's the total impedance. Okay, so this is all good. I have now found the total impedance. I could call that the total impedance. Is that what we're looking for with this problem? Total impedance? No, we're not. So what we're looking for is we are looking for the output voltage. My goal is to find output voltage as a function of input voltage. So right now, I don't have anything with output voltage. That's kind of a problem. What is output voltage equal to? The voltage across R1. Thank you. So now let's define, this would be KVL 2. Is V out is just equal to the voltage across R1, which is equal to R1 times the current. That's great. So our final goal is to figure out V out over V supply. We're in the S domain. And so we have an R1 times the current all over. Here's where my supply voltage comes in. So we've got R1, R2, CS plus R1 plus R2 all over R2 CS plus 1. And here's my current. I'm taking output voltage over input voltage. And we should be able to get to a transfer function. The nice thing about this is that the currents are going to cancel out. And then basically I'm just going to move this numerator up here. So when you divide by a fraction, the denominator comes up to the top. So our final transfer function is going to be R1, R2 CS plus R1 all over R1, R2 CS plus R1 plus R2. Okay. So again, if you don't like this, you don't have to use it. Both methods do require KVL. In this case, I didn't need to do a KCL because I was able to just bring those together, make a Z equivalent. Sometimes it's not like that's not always the case. Sometimes I do need to keep things separate. Sometimes I will use a KCL with impedance, but it can be a nice way to just get it quickly to the S domain, simplify the circuit a little bit, and then go from there. But ultimately, a lot of the same rules still apply to get to our final answer. There's many ways to mess up the algebra, so take your time. Try to do each step at a time, not trying to save it all till the end to then factor out and everything. Question? No? Okay. Let's see. Oh man. I guess we'll do this one. I want you to start full body on this. You know what? No, we just did it last class. What do we? We're just gonna copy paste. We already. You know what? Okay, we're gonna do it. I want you to actually try this, but what we're gonna solve for is EC. So the other option here, with respect to EN. So we can skip the first couple steps of body. We already know the order. We already know. Now you can change up the circuit diagram if you want to a little bit, but we're going to try to solve for EC with respect to EN. So you can start with the diagram. So you can work on a different diagram if you want to, and then we'll finish up with definitions. But I'm going to give you some time. I want you to try, even if you hate the impedance method. I just want you to try it because you might like it. My kids like reading Green Eggs and Ham. Okay, you might like it, even if you've never tried it. Like, go for it. You might like it in the class. You might like it next to glass. But we're going to try to solve for differently than last time the voltage with respect to the input voltage. And these are on the equation sheet. So inductor impedance is LS. Resistor is just R. Capacitor is 1 over CS. Telling students, I don't know, what have I been telling you? Take your time. Uh, do each part individually. Every impedance, when you add them up, someone asked if adding in series is the same as adding parallel. Let me just give you an example. Let's say I have this, I'm trying to find Z. Why can't we just do Z equals 5 plus 5? Well, if I have 5 plus 5, that's equal to 10. But if I add up the reciprocals, then Z is equal to 5/2. So those are different. So that's why being careful with your reciprocals. I've had some people that, they add stuff up, they take it to the -1, but they don't really know what to do with it there. So just trying to do each part together. Like, for example, in this problem, I would do these two first. They're in series. So I would do that one first, just all by itself, just to find one Z equivalent. And then you can think about the next step, which is combining all of them. Well, if you did it all at once, it's possible to get it right, and it's also more possible to make a mistake. Yes. So I would encourage you to just try to combine what Z equivalent should be. I haven't done it yet. I, I actually haven't done it. It's a great question. Should we leave the capacitor out? Because you could create a total impedance, but do you need to do that? You might need to do a total impedance. I think you might. I think you might. Yeah. So, step one, I would say create some kind of Z equivalent 1. And then step 2, then you can combine them all. And actually, I can treat this as an impedance as well. And then after that, you've got the same current going through here. But I would do 2 steps. Not trying to do it all at once, because that's where I see a lot of mistakes. Trying to get there. Do you like impedance? Do you like it better than the other? Do you like impedance? Sometimes. Yeah, no, I agree. Hey, and like a good thing is if you kind of get familiar with this, you can do both options on the test to kind of double check yourself. Hey, I'm going to try it this way, then I'm going to try it this way. Uh, if you have time for it. And the other question is, if they're different, which one's right? That's also like you leave both and you hope one of them's right. Yeah. That's to leave 4 different options just to be safe, Yeah, yeah. Like if it doesn't have an S in it, I'm getting rid of it, like cross that off. That one's not right. I need to have some kind of S. Okay, so I've kind of done the body diagram part. You can do this, then you can do this. You should be working on your definition. So like, what is Z equivalent 1? And then what is Z equivalent 2? And then from there, we're trying to figure out the voltage of the capacitor with respect to the input voltage. That's the transfer function. What is the order of the transfer function? It is second order, yes. So it's second order. We figured that out last time because I've got a capacitor and an inductor. Those are both first order. 1 + 1 = 2. I'm going to give you a little bit more time, and then we'll do it together and take a break. We do it together. Is it time? You can keep working if you like. We're going to do definition. So first off, I'm going to turn this into Z equivalent 1. So resistor, inductor, capacitor. So Z equivalent 1 is just they're in series. So that just means I add them. So ZR2 plus ZL, that equals R2 plus LS. And really, I always like to put the higher order first. I like to put my S first, especially when I get to my transfer function. We should go from highest to lowest. So I'm just going to flip that around. So Z equivalent 1 is equal to LS plus R. How you feeling? Series, not too bad. All right. The next step is I want to combine all of this into Z equivalent 2. And now I'm working with parallel. So we've got 1 over Z equivalent 2 is equal to 1 over ZR1 plus 1 over Z equivalent 1. So this is 1 over R1 plus 1 over LS plus R2. This is going to be a little bit tricky, but we want a common denominator. So for example, I'm going to multiply this by LS plus R2 over LS plus R2. I'm going to multiply this by R1 over R1 to get common denominator. So my denominator is going to be R1 times this. And then we're going to have this plus this because we just have ones up top. So this will be LS plus R2 plus R1 all over R1 times LS plus R2. So take your time with it. And, you know, if you want to write out just kind of like I did. So I'm multiplying this by this to get a common denominator. This is my common denominator, so I got to multiply both sides by different things. As long as it's, you know, I'm just multiplying it by 1. There's no problem with it. And now we can get, is that our impedance? No, that's not our impedance. Impedance is, we got to flip it. So we have R1 times LS plus R2 over LS plus R1 plus R2. Or we can work it out if we want to. Like that. So now I've got everything combined into one. Let me just draw the tiny circuit right here. This is my Z equivalent 2. This is my Z for the capacitor. And that means now I have all the same current. I don't have to worry about different currents. That's the nice thing about bringing that all together. Questions? Just be careful. You know, a lot of mistakes in this class, not just the setting it up and diagrams, but the algebra. Just making sure you carry stuff over, everything like that. I might have made a mistake. No, I'm not trying to. So if you catch any mistakes, you got some similar, maybe? What? Okay. So yeah, I didn't really kind of changed up my notes right before class. So that's my Z equivalent 2. So now let's do the KVL. I've got my system right here. So if we do a KVL of the loop, I have En minus the voltage across Z equivalent 2 minus the voltage across the capacitor equals 0. So therefore En is equal to Z equivalent to voltage plus voltage of capacitor, and using the transforms, they both have the same current. So this is Z equivalent to times the current plus the impedance of a capacitor, which is 1 over CS times the current. And so we can combine these because they have the same current. That's what En is equal to, because it's really the total impedance. So I'm just adding these in series together. So I get Z equivalent plus 1 over CS. This gives me my total. You can think of this as total impedance. And let's look that out a little bit. So En is equal to, I've got this R1 LS plus R1 R2 over LS plus R1 plus R2 plus 1 over CS. Great. That's good. You know what I should do? You know what I should do? Common denominator? Oh, man. Okay. So, more algebra. So I'm going to multiply this by CS over CS. And I'm going to multiply this by LS plus R1 plus R2 over LS plus R1 plus R2. Okay, so these all are going to get multiplied by CS. My denominator is going to be the same. It's going to be CS times all of this. And then we're going to add it that way. So we get R1L or CL S squared plus R1 R2 CS. So that's this first, then this first, or second. And then I'm going to have all of this as well, plus LS plus R1 plus R2. This is multiplied by I. Now we have CLS squared plus R1 plus R2 times CS. Okay, so you can definitely, I mean, either way you do this, there's going to be algebra. We did algebra, and the last time it wasn't as right at the beginning. Because we're changing it to Laplace transform, we're able to combine some things that allows us to do algebra a lot earlier. So complicated. So just be careful, take your time with it. Again, I may have made a mistake because there's a lot of terms here. So I just try to be careful with it as you go. But this is still the Z total. This is the total impedance. All of these elements together, this is what it looks like, which is close to our transfer function. If I was just looking at the current, like what is the current with respect to the input voltage, that would be this transfer function. But the problem actually asked for, or what I was looking for is I want capacitor voltage with respect to En. So we're almost there. Question? Yeah. And with the algebra. Before we get to the last step, I need to figure out what EC is equal to. Can anyone tell me what EC is equal to? The voltage across the capacitor? We actually used the definition before right here. So for any voltage, we can look at it as the transform, the impedance multiplied by the current. So it's 1 over CS times current. So I got to go to the next slide. But the last step is I now just take EC over En. I have a definition for En that involves the current. I have a definition for the capacitor voltage, which involves the current. Those currents are going to cancel out just like the last problem. And we should be able to get to 1 second order transfer function relating the two. Okay, so I'm going to have to flip back quite a bit, but we can just start with EC. So EC over the input voltage, I have 1 over CS times the current. That's my capacitor voltage. Now I'm going to put in my En, which is all of that. R1 CLS squared. I combine my S terms. R1 R2C. I missed the C right there. That's my S term. Then we've got R1 plus R2. And then You know, I multiplied CS to all of this, but I think it actually makes more sense if I keep it separately, and I'll show you why. So if I have CS times LS plus R1 plus R2, that's what I'm going to put in here. CS LS plus R1 plus R2. So, oh shoot, this also is multiplied by the current. So the currents do cancel out. Currents cancel out. And then the CS's also cancel out. So this cancels out with this when I'm dividing it. And so what's going to happen is that the transfer function, this bottom portion, the denominator, is going to swing up to the top. So we get LS plus R1 plus R2 all over R1 CLS squared plus R1 R2 C plus L times S plus R1 plus R2. And that is our final answer. So yeah, it's a lot of algebra. Again, if I did it the other method, you know, we do our KVL, KCL. We'd have a lot of different equations. We would eventually get to two equations, and then we would put it into the S domain. Dots become S's, and then we plug them into each other, and that's where the algebra occurs as well. So the algebra is here. In this case, we're able to combine these, but that's, you know, effort in itself just to get to that correct, the equivalent. Then we can get to our second order. So one thing to check, it's all positive, it's stable. Denominator is stable, that's good. It is second order. It actually involves every single component. It should. It should have all the R's, L's, and C's. So we can always double check our work with these kinds of problems. Okay. Any questions? Yeah, yeah.
I did like multiply the CS thing.
Okay.
Like, is that just a practice to know like how?
Oh no, I just did it to make our notes a little bit easier because it's fine to multiply the CS by that and then recognize that, oh, that's all. So I just changed it back to being separate to make it easier for notes wise. Yeah. No, I didn't know that. I didn't know it was gonna happen. That's why I didn't do it initially. Yeah. Other questions? Question. Let's take 5. I'm gonna go. I'll keep this slide up here. If you got any questions about this, we can talk about it. Let's take 5. It's 8:20. Let's come back at 8:25. We're gonna cover one last thing called motors. And if you can pull your computers out, we're gonna do a little SimScape too. Well, like for the mass, for J, input out. For the mass, if theta changes, it's going to push the mass and the output mass. So, yeah, I guess this could be right for J. This is the mass, it should be theta and X out. They're kind of inputs and outputs. Okay, if you could pull up MATLAB, we're going to be using it soon. Our last thing today, so again, if you don't like impedance, that can be the last time you ever do it. Okay, it's just an option. It's a way to look at a system. All of us have different circuit training. Now, for some of this upcoming, you don't have to write this down. I'm going to give you an introduction to kind of electromagnetic, what's going on in these. But obviously, we work with a lot of different electromechanical systems, any kind of motor, solenoid, actuator, whatever. Some of you, are you working with these in your capstone at all? Nothing with electricity or mechanical. Oh, wow. Okay. Well, a lot of sensors. You got some sensors. Now, sensors take a physical change and turn it into an electrical signal. Speakers, microphones. So by combining different mechanical electrical elements, we can construct any kind of devices. It's always converting energy from one form to another. So a sensor is converting physical to electrical. A motor is taking electrical and changing it to a physical. So it's a transfer of energy. Now, how does it do that? So this is what I'll talk about for a couple slides. Is it's all based, a lot of it is based on magnetism. So it's creating a magnetic field. That's how you can transfer electrical energy to mechanical. Now, both Newton's and Kirchhoff's laws are obeyed. So with electromechanical devices, you kind of model them as two separate things, and the circuit has to obey Kirchhoff's laws. The mechanical side has to obey Newton's laws. So don't write any of this down. Is that okay? Don't write it down. Don't write this down. I don't want to get hung up on this. It's not like you have to understand it. I have a video that's going to explain it a little bit more, but there's three basic relationships. The first one is when I send current through a wire, it creates a magnetic field. And the direction, you can use your right hand rule. This is important to know, like when you're setting up equipment in a large manufacturing area, you don't want a 480 volt power line to be right next to some very sensitive sensor wires. Why is that? Because it's creating a magnetic field. So you got to have separate conduit. You got to make sure they're separated because the magnetic field can interrupt, that sensor data, make it off. Okay. Another thing, I think maybe we know that, but one other part of this is a little bit different. Let's say I have a permanent magnet right here. So I got north, south. I have my direction of magnetic field. And I have a wire. If I send a current through that wire, there will actually be an induced force. It's going to want to move. There's a force applied to that, which is the cross product. It involves the magnetic flux. It involves the length of the wire and the current. So the more current gives you more of a pull upwards. So you might not be as aware of that, but it's one of the three laws that helps DC motors work. So the video will explain it. And then, lastly, let's say I don't even have a current. I don't have a current, but I'm moving a wire with a certain velocity up through a magnetic field. That will actually create a voltage, induced voltage. And so that's all based on the velocity, the length of the wire. And what we call that And what the video is going to talk about is back EMF. So back EMF is a voltage induced just by the motion of a coil of wire within a magnetic field. So I think I'll let we'll get to the video again. So motors operate on those three things. They involve sending a current, they involve creating a force, and they also create some back EMF. They create a voltage by that motion. And so if you've ever pulled apart a drill or whatever, what you have is you've got your magnet creating the magnetic field. You have your armature. So this is the rotor with all the coil of wire. Have you ever pulled a drill apart? Just be curious. I mean, it's just a lot of wire right there. So all that wire, those windings, that's where all the current's going through to give you that rotation. And let's see, the torque. If I want to pull the trigger, I want to get some torque. That is equal to B, which is magnetic field, the length of the wire. So the more wire I have, the more torque I'm going to get. Current. So if I can increase my current, I increase my torque. And then the radius. So that's all based on, the radius of that rotor. I'm going to show you a video, and then we'll talk about how it pertains to our class.
Automobiles and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field. In the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow toward. This ensures that the torque action is also in the same direction throughout the motion. The coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor construction: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF.
Hey, that's what we talked
A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the motor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and
DC. Anyways, I thought that was a pretty good video. But basically, as it's turning, there's back EMF, and that back EMF is a voltage that actually opposes the input voltage. So the faster it spins, the more back EMF you have, and that's part of our modeling is to model that voltage. So here's the equation right here, and it's on the equation sheet. This is what we use. This is called back EMF. So remember, E stands for voltage. It's very simple. This is the constant KB. It's called the back EMF constant. Now, what it's made up of is it's made up of what is the magnetic field, what is the length of the wire, what is the radius of the rotor. But none of those change. And so we're just going to combine it all into KB. That's our back EMF constant. We multiply that by the speed. So theta dot is the speed of the motor. Theta dot, radians per second. And so this is how we can find the voltage. So this is going to be the volts opposing the input voltage. As the speed goes up, you have more back EMF. So that's one of the equations we're going to use. That's going to go towards our circuit. This back EMF constant is also used to figure out what our torque is. And so on the next slide, we've got another equation. And really, Km is the same as Kb. So I like using this equation. That back EMF constant is the same thing that's going to relate us from the circuit to the mechanical side. The motor torque is equal to that back EMF constant multiplied by the current. In the book, it lists it differently as the motor torque constant, but those are the same thing. So Kb equals Km. Okay, so what we're going to do is we're going to do a quick, we're going to model a motor. It's an electromechanical device. We're just going to look at each part separately, and then we're going to try to put it together in Simscape because Simscape has motor blocks that we can use. You good? Everyone good? All right, let's do a problem. This is how you typically see a motor listed, especially in the textbook. This is, I forget what chapter this is from, but what we've got going on is this is actually the armature. This is, if you think about this, this is like the coil of wire around the rotor. So there is a large length of wire here. That length of wire has some resistance. The longer the wire is, the more resistance. It has some inductance because it's a coil of wire. And this is where our back EMF is. So we're going to model that as part of our circuit that goes into the rotor as well. So if we're thinking about a drill, I'm giving it some input voltage. And then what we see on the other side is we see this start to rotate. And we can look at the torque from there. First step is breathe. Okay. I think we can do it. We have some equations. It doesn't change much of what we're doing. It's just adding an equation to it. What would you say the order of the system is? And to make it a little bit easier, we can look at the circuit side and then the mechanical side. What is the order of the circuit? First order. Because I got one inductor. Each inductor capacitor gives us the first order. And then the mechanical side, the rotation, look at degrees of freedom. It's going to be second order because we have 1 degree of freedom. We have one object, one motion type. So what would you say the total order of the system is? Right, it's third order. No one actually answered. We just add them together. So in total, it's a third order system. We're really just gonna look at them separately. I'm gonna make a model for the circuit. I'm gonna make a model for the mechanical part. We're not going to really combine them, but they do have some overlap. They do have some. They do affect each other. So now we get to the body diagrams for the circuit. It's all the same current, so it's basically ready to go. For the clinical side, you can look at it from either side. I'm actually going to switch it up. I'm going to look like I'm looking at the end of the drill just to see how it's moving. So I'm going to draw it like from that perspective, which means theta is positive counterclockwise. So if I'm looking from this perspective, I've got theta, motor torque, same direction, load torque going opposite from it. And which way should the friction act? We do have some friction in the drill. Clockwise, okay. Because we want to go against the positive motion, positive displacement. So might have thrown you off that I'm looking from this direction, but that's okay. If I'm looking from here, I've got one positive motor torque, the other two are negative. They're fighting against. Okay. All right. Now let's try this out. Inputs and outputs, we can look at both the circuit and the mechanical. The circuit, we have E in, the output would be the current. Because we have the inductor, I could write it as I sub L, just because I have that inductor there. Mechanical, I have motor torque, and the output would be, what's the output of the rotation? Theta. Great. Now we have some equations here where we're going to relate some of this. So, for example, theta is actually going to affect the current, and that's based on the back EMF. The more it spins, the less current I'm going to have. Motor torque is related to the current. So the more current I have, the more torque I have. So there is going to be some crossover between these two. We're going to see in the equations that we find. So that's a little bit of what's going on here. We could also look at input is the load torque. If I'm trying to put a screw into the wall, there's some load torque there as well that I have to overcome. So the more torque there is, the harder it's going to spin. And again, I just want to say, for homework and tests, it's not important to get every single one, but trying to have an idea of what's going to be in our final equation. It's just really trying to set up what those equations should look like. Questions? Okay. Next up, definitions. So we can look at the circuit side. We can look at the mechanical side. And for the circuit, we've got, our typical, like, Ohm's law. I'm just going to call it IL. We have our voltage. And you could use impedance on this as well. You could have an LS plus R. That's totally fine. I'm just going to go back to what we were using with last time in class. We just wrote down the definition for back EMF voltage. Maybe we wrote it down. It is on the equation sheet, so if you didn't write it down, you don't have to memorize it. But what is that equation? Oh, it was on the, I had a box on the slide. What? That's fine. It's on the equation sheet. It is back EMF constant times theta dot. So the faster this thing spins, the more voltage we get out of it. And any other definitions for the circuit? Anything that might be helpful? We have the three different elements here. I have the inductor right here. Voltage related to the current. But like, what's our Newton's second law for the circuit? Like, how are we going to put them all together? KVL. Thank you. So KVL, what we get is our input voltage minus resistor voltage minus inductor voltage minus back EMF. Because remember, back EMF is going to fight it. It's not going to help it. It's actually going to fight against that input voltage. So we can say that En is equal to the sum of all of those voltage drops. That's the equation we're going to use on the next slide once we start putting it all together, diminish. But for now, we got everything we need. There's no current law, nothing splits. Everything's the same current. Okay. Now mechanical. Let's start with Newton's second law. Sum of torques equals J theta double dot. That's my starting point. Motor torque. Maybe we didn't write that down. So this is new based on the motor. This is new based on the motor. The motor torque is equal to that same constant, back EMF constant, multiplied by the current. So Those are my two definitions, and that is what ties it to the circuit. That's what this ties it to the mechanical side, so we can use that just as the connection point right there. The last thing we need is friction, and that is just going to be B theta dot, because it's just dependent on how fast the rotor is turning. We're going to have some friction there. Load torque, we don't need to define. That's just going to be an input. Okay, so we're going to go to the next slide. We're going to put it all together, and then we'll build this in SimScape because they've got a DC motor block. I'm going to take this. I'm going to plug stuff in. We're going to get 1 second order equation here for the motor. We're going to get one. Wait. This is first order. This is second order for the motor. So in total, third order. Does this? You don't have to understand electromagnetism. Does this make sense? Just those two definitions, tie it together. Okay. So for the circuit, we have En is equal to ER plus EL plus EB. Now we put our definitions in. And I have two different dots. We kind of talked about that last time in class. It's not really what we want. But at this point, I can't really get away from it. What I would say is that for the circuit, we identified the output as the current. So I'm going to keep the current on one side. I'm going to put everything else on the other. So what we get is En minus KB theta dot is equal to, I'm going to start with the highest order, LIL dot plus RIL. That's equation number 1. So my output is over here, current. And the current is related to the difference between the input voltage and the back EMF voltage. The faster it spins, the less current I'm going to have. It's going to change how it flows. I don't really like two different derivatives, two different variables with dots. So I don't know if I can change it, but we'll see what happens on the mechanical side. Mechanically, we have sum of torques equals J theta double dot. This is equal to motor torque minus friction minus load torque. So we can put in our definitions. So looking at the diagram, what's positive, what's negative. The output is theta, so we can get all the thetas to the same side. And that gives us an equation that looks like this. So I have one first order equation, I have one second order equation that models the motor. So not a whole lot of new stuff. It's just the way that these tie together. And I've talked about it a few times. I really like this theta dot. I don't like having two derivatives in the same equation. So is there a way that we can change that? Any ideas? Small angle approximation for a drill. I think it's just going to keep going around and around, but let's get a guess. Yeah. Solve for KB and plug it in. Okay. So we could try to combine them all by solving for KB, because that is a like term. But I think at that point, I'm still going to have an IL dot and a theta dot in my final equation. So I don't think that's, I like both the ideas. They're just not quite right. Do I have any just plain old thetas in any of these equations? I have any just purely displacement? And the answer is no, I don't have any thetas. So what we can do is we can kind of change the goalpost instead. We can change theta dot to omega, and we can change theta double dot to omega dot. Instead of looking, because usually with the drill, I'm not so super concerned about where the point is at any point in time, like what is theta. It's usually about the speed. So we can change this equation to j omega dot plus b omega equals this. So that actually takes it to a first order equation. And then we can do the same thing for this one. We can substitute in just omega for the speed. So that was like homework 1, where you first did it in terms of displacement, then they asked to do it in terms of velocity. So I can always change it. And that way now I have nicer looking equations. I don't have 2 different derivatives going on there. Okay, so in total, it's a second order equation. This right here is what ties the mechanical to the circuit. This right here is what ties the circuit to the mechanical. That's really what's going on, is that current is driving the torque. Based on the torque, I get a speed. The speed then goes back to the circuit to be like, hey, we got to slow down. We can't get as many amps as we had before. So, wow. Can we make a transfer function? You talked about substituting. I can't really substitute because that's going to give me 2 different derivative terms. So we're just going to leave it as is. There's no transfer function. It is linear, but we would have both an omega dot and a current dot. And there's not really a way around that. So I can't really solve for just one because there's that feedback one to the other. So we're going to skip that for today. The other thing is we do have 2 different inputs. So we also have a load torque and an EN. So based on these 2 different inputs, I can't also do a transfer function. 2 different inputs. Okay. Now I want to model it. So this is the mathematical model of the motor. We're going to use it occasionally, but in the homework, so there is a motor thing, so you're going to, a lot of similar stuff to this. But it also asks you to do a SimScape. So today, if we can get a SimScape model going, that also helps for some of your homework. That's not due this week, it's due next week. So what I'd like to do is create the SimScape model of this. That's the last thing we're doing today. If you get it done pretty early, great. But it might take a little bit of time to get it figured out. I just want you to get closer to figuring it out for the homework. So in Simulink, so I would open Simulink within MATLAB. I would do new from template, SimScape. I would do either mechanical, rotational, or electrical. So that's going to get you, a few things. For example, I did electrical just as a starting point because the motor involves those 2 different parts. There is also a DC motor, but you should have that block. If you don't, it's under electrical. So if you don't have the SimScape electrical add-on, you'll want to add that. It shouldn't take too long to download. But that gives you a DC motor. DC motor is great because you can put a lot of the stuff in here. You can connect it. I can help you out with it. I just want you to try to set up the same motor as what's going on here. So you're going to connect the circuit. You're going to connect the voltage source. and then look at the output.